Chapter 16.5, Relative Motion Analysis, Velocity. Let's do a math review, reviewing vector cross products. First of all, what is a vector cross product? It's a way of multiplying two vectors together that will result in a third vector. Now that's different than a vector dot product. A vector dot product multiplies two vectors together and results in a scalar quantity. A cross product, however, is multiplying two vectors together resulting in a third vector. Let's do an example. Let's say I have these two vectors, 3i plus 5j minus 6k, and vector b is negative 2i plus 4j plus 1k. And let's find vector a crossed with vector b. Here's how we do this. We set up a matrix and then find the determinant of that matrix. There would be the matrix. And then we remember that that top row has to have alternating signs. So the matrix is, the first row of the matrix is ijk with alternating signs. The second row of the matrix is the first vector that we're crossing. And then the third row of the matrix is that next vector, vector b, that we're crossing. And then if we want to find a determinant, the first thing we do is we say, okay, the I component of the new vector, we would have to cross out the ith row and column, and then multiply it by the determinant of that smaller 2 by 2 matrix, which is 5 times 1, subtract 4 times negative 6. So the ith component of the new vector is 29i. The j component comes from taking the negative and crossing out the jth row and column. So notice we've put in the negative and we've crossed out the j row and column, and then we take the determinant of that small 2 by 2. We take the 3 times 1 and then we subtract out the negative 2 times the negative 6. So the j component of the new vector is 9j. The k component of the new vector comes from crossing out the k row and column and taking the determinant of that small 2 by 2. The 3 times 4 subtract the negative 2 times a 5. So the k component for this new vector would be 22k. So the a cross b then would have an I component of 29i, a j component of 9, and a k component of 22. That's the cross product. We take two vectors, multiplied them together in a cross product, and we get a third vector. Now let's review rotation about a fixed axis. If I have this rod BA rotating about point A at 5 radians per second, determine the velocity vector of point B. Well, of course, velocity magnitude is omega times r. In this case, it's 5 times 3, which is 15, and we know that that's in the j direction, just because we look at it and we know it's moving directly upward. So that's one way we could write that vector, is we could use some trigonometry. Let's do this now with this up at 30 degrees. Again, we know that that's 15 meters per second. Omega times r, 3 meter radius times a 5 rad per second, that's 15. But now it's pointing in a direction that's not directly in the I or j direction. So we can use some trigonometry. We could say that the x component would be 15 sine of 30 degrees, and the y component would be 15 cosine of 30 degrees. Now remember that this angle up here is the 30-degree angle. That's why this side was the sine of that angle, this side was the cosine of the angle. So we could write this vector now as 7.5i plus 13j. So that's one way to write that velocity as a vector. So we could use trigonometry. But there's an easier way. Let's determine this velocity vector at point B, but let's do it using vector math, or the vector cross product method. there's my omega vector, and we use the right hand rule to determine that. Use your right hand, your fingers curl in the direction of the 5 radians per second. Your thumb points into the board, which is in the negative k direction. So the omega vector is a negative 5k. And what about the r vector? Well, the r vector we can find by taking the radius of 3 meters, and the x component is the 3 times the cosine of 30, and that's in the negative direction. And the j component is the 3 times the sine of 30, and that's in the positive j direction. So that's our omega and our r vectors. If I want to find velocity as a vector, well, of course, I can multiply the omega times the r, but if I multiply them as vectors using the cross product, now I will get the velocity out as a vector. So let's take the omega vector crossed with the r vector, and if we do that, we have a resultant of 7.5i plus 13j. That's exactly what we came up with using the trigonometry approach on the last slide. Okay, now let's also review this relative motion, the school bus example. If you remember, a school bus, if there's a boy that's on a bus, and the bus is traveling 55 miles an hour, and this boy is running down the aisle at 5 miles an hour, we developed an equation that said that the boy is actually moving at 60 miles an hour. And we found that by saying, well, the actual velocity of the bus plus the boy's relative velocity on the bus, if we added those together, we got the total velocity of the boy. We called that relative motion, a relative motion equation. You could also consider that an equation of superposition. We basically superimpose the boy's velocity on top of the bus's velocity, and we added those together, superimposed them. Okay, so now let's combine these together. What happens, there's a wheel, and this wheel, the center of the wheel is moving at 5 meters per second. But the wheel is also rotating at 50 radians per second. So the question might be, how fast is the top of this ball moving? So think of this as a ball flying through the air that's also spinning. A ball that's flying directly straight forward and spinning at the same time. This should start you thinking on the method of superposition. We could superimpose the rotational effect superimposed on top of the velocity, the linear velocity effect. So let's do this. We're going to superimpose them. First of all, let's do the velocity due to translation only. Well, 5 meters a second. Now let's look at the velocity due to rotation only. In other words, if this was only rotating at 50 radians per second, the velocity of the top would be omega times r, or 5 meters per second. A 0.1 meter radius, omega 50 radians per second, so that's 5 meters per second. So now we could superimpose the two on each other. If it were only translating, it would be going 5 meters a second, and if it were only rotating, it would go 5 meters a second. So therefore, the total must be the 5 of translation plus the 5 of rotation, 10 meters a second. Let's do another example. Here's a rod that is translating and rotating at the same time. Think of a rod and you throw it and it's flipping end over end through the air as well as translating. If we knew that point A was traveling at 4 meters a second in the direction shown there with the blue arrow, and it happened to be rotating at 5 radians per second, let's find out the velocity of point B. First of all, let's look at the velocity due to translation only. So there's the translating component of velocity, and so if it were only translating, then point B must also be going in the same direction. So let's draw that as a vector. That would be 3.5 in the I and a -2 in the j. Okay, now let's pretend that it's not translating, but it's only rotating, rotation only. Now let's find out what point B is doing. We know that it's 15 meters a second in that direction, but let's write that as a vector. That was, we could use either trigonometry to find that 7.5i and 13j, or we could use the cross product and cross the omega vector with the r vector. There's the omega vector, there's the r vector, and the cross product would be the 7.5 and the 13. 7.5i plus 13j. So the velocity at A is just the translation, and the velocity of B with respect to A means pretend that A is fixed. What is B doing from A's point of view if A were fixed? Okay, now let's combine the two due to both translation and rotation. There's the vector due to translation. There's the vector due to rotation. Now if we add those two together, superimposed upon one another, the red is the total velocity of point B. There's our relative motion equation, or we could call it the superposition equation. We're taking the translational velocity and adding to the rotational velocity to get the total velocity at point B. So if we add the vector A, which is 3.5i minus 2j, to the vector 7.5i plus 13j, we will get the total velocity at B, which is 11i plus 11j. Now we know that if that rod were flying end over end through space, that point B happened to be moving at 11i and 11j, or a magnitude of 15.6 meters a second. Okay, here's an example now of how we can put all these things that we know together into solving a mechanism that may have 3 or 4 components. Here's a little video showing how such a mechanism would operate. We see that one is driving and the other is being driven, and the rod connects the two. Looks like the small circle is driving and the big circle is being driven, and it basically rotates until it gets to a binding point, and then we'll reverse it. And we're seeing that the rod is translating and rotating, but the two circles are only rotating. So we can see how for the rod we may need to do a method of superposition to find out velocities on the rod. So let's do this problem. If disk D has a constant angular velocity, 2 radians per second, so this disk here, this disk right here, has a constant angular velocity of 2 radians per second. I want you to determine the angular velocity of disk A here at the instant shown, where the rod happens to be in this particular position. So let's take a look at how we would do this. Step 1, let's find the velocity of point C, and let's write it as a vector. So if the omega of disk D is rotating 2 radians per second clockwise, and this is the velocity that we want to find, well, we could take the omega vector, cross it with the r vector to point C, and find velocity c as a vector. So let's do that. There is our matrix that we'll set up, and if we did the matrix math, we'd find that the velocity c would be 1.3 in the I and 0.75 in the j. So we know that that is the true velocity of point C. Okay, now let's do step 2. Now let's find the velocity of point B with respect to C, or in other words, as if C were fixed. So we're going to draw this rod, and we're going to pretend that C is fixed. So we're just going to pretend that it's just a pin connection at C and it's fixed. And what if the rod were rotating with that omega rod CB? Then how fast would B be moving? Now this is only the velocity of point B on the rod if the rod were fixed. So this is only the rotational component. So velocity B as if C were fixed would be the omega of rod CB crossed with the R of CB. So there's our matrix that we set up. And if we do that cross product, we'll come up with this velocity of B as if C were fixed would be negative 1.73 times the omega CB in the I direction and a negative omega CB in the J direction. Notice the omega CB we don't know. We don't know how fast rod CB is rotating, but that's okay. It's an unknown in the equation. Okay, now let's look at step 3. Now let's find the actual velocity of B. Well, to find the actual velocity of B, we take the translational component of that rod, which happens to be the velocity of C, and we add to it or superimpose onto it the velocity of B as if C were fixed, or the rotational component, and if we add the two together, we will get the total velocity of point B on the rod, which is shown there as this vector. And notice there's an unknown there. We don't know the omega CB still. So basically we went from point D and worked our way from point D. We started at point D, worked our way to C, and then worked our way to point B. So steps 1, 2, and 3 started with the known, with this known omega, and worked our way up to point B. Now, step 4, we're going to start with point A and work toward B. And we'll notice that A really is fixed, and it lies on disk A. So if this is what we were looking at, and we had omega A, which is unknown, let's find velocity B. We can see that velocity B is simply the omega of A crossed with the radius from A to B. There's our cross product matrix that we set up, and we find that velocity B on the disk is 0.35 omega A minus 0.35 omega A. Now we have, if we look here, we have the velocity of the disk of point B on the disk and the velocity of point B on the rod. And we know that those two are the same point. So we could set those vectors equal to each other. What we're going to do is we're going to set the I component equal to this I component, and we will set the J component equal to this J component. And if we set both of those components equal, now we have two equations, and we have two unknowns, the omega A and the omega CB. So let's do that. Since point B is on the rod and is also on the disk, we're going to set those two velocity B equal to each other and solve them simultaneously. We find that omega A happens to be 0 in this instance, and the omega CB is 0.75 radians per second. So we've solved that problem, and just to review, the way we did it is we started with the disk where we knew the omega, and we worked toward point B. And then we went to the disk where we didn't know the omega and worked toward point B. And once we found two equations for the velocity of point B, we set them equal and solved, and we were able to find both the unknown omegas. Okay, now let's talk about how this technique, we call it the relative motion velocity technique, how this could be useful in solving planetary gear problems. This is a planetary gear that a group of students did for a project, and this planetary gear will have a ring gear. It will also have a sun gear at the center, and it will have planet gears, maybe 2, sometimes 3 around the outside, and those planet gears are always connected together with what we call a planet carrier bracket. So let's take a look at some of the benefits of a planetary gear system. A planetary gear system allows you to have multiple different gear ratios based on which of those items are held fixed and which are driven. For instance, if I were to hold the ring gear fixed and drive the sun gear, let's take a look. We'll look at this little video here. The sun gear is going to be driven, but the ring gear is going to be held fixed. this outer ring gear won't be allowed to move. The inner sun gear will be driven, and we want to see what this planet carrier does. In other words, let's take a look at, there's a blue dot here on the sun gear, and then there's a blue dot here at the center, which will move around based on how this planet carrier is rotating. And this will have a gear ratio of a 4.8 to 1. I drive the sun gear 4.8 times around, and the planet carrier will only go around once. So if you look at the handle that he's holding onto, that's fixed to the sun gear, and the other handle that's rotating is fixed to the planet carrier, and you can see that there's a 4.8 to 1 gear reduction. What if we drove the planet carrier and held the ring gear fixed? So instead of driving the sun gear, let's drive the planet carrier now. That's this video here. Basically, we have the opposite. We have now a speed increase rather than speed decrease. For driving the planet carrier, then the sun gear will turn 4.8 times faster than the planet carrier. So in this case, we have either a gear up or a gear down. What if we were to drive the sun gear, but now we're going to fix the planet carrier and see what would happen to the ring gear if we let the ring gear rotate? That would give us a 3.8 to 1 ratio, and it would give us a reverse transmission. Notice he's spinning the sun gear counterclockwise, but the ring gear is turning clockwise. And we have a gear reduction of a 3.8 to 1, and that's a reverse transmission. If we hold that planet carrier fixed, drive the sun gear, 3.8 rotations would result in 1 rotation of the ring gear in the opposite direction. Here's another scenario. What if we were to drive the planet carrier and fix the sun gear? Now let's look what happens there. Now we have almost an overdrive situation, a 1 to a 1.26. So now if you can see that he's holding the sun gear fixed and driving the planet carrier, and that results in almost a 1 to 1. The ring gear actually goes faster than the driving planet carrier. So this is how this is the basis of a automotive automatic transmission. An automatic transmission will have hydraulics that will clamp down on certain aspects of a planetary gear. Maybe it will clamp down on the ring gear and hold it fixed, or maybe it will clamp down on the planet carrier and hold it fixed. So in an automotive transmission, there are several planetary gear systems with several hydraulic clamps that will clamp on different aspects of the planetary gear, which allow you, without even disengaging the gear teeth. So the gear teeth never come out of mesh with each other, and we get several different gear ratios, including a reverse. So let's do this as an example problem. Let's say that this planetary transmission has a fixed sun gear, so we're not allowing the sun gear to rotate. The planet carrier is being driven at a omega of 8 radians per second, and we want to determine the angular velocity of the ring gear. So this case, we're holding the sun fixed, driving the planet carrier bracket, and seeing what happens to the ring gear. So let's do step 1. First of all, let's find the velocity of point C on this planet carrier bracket. There's the planet carrier bracket, and that center point E is actually fixed. It's not translating. And we have this omega CD of 8 radians per second. So that's being driven at 8 radians per second. And of course the velocity there at point C would simply be the omega times the radius. So velocity at point C is moving at 1 meter per second. Okay? Now knowing that the sun is fixed, let's find the omega of the planet gear. So we know that the sun gear is fixed. So we're finding now the omega of the planet. And if the sun gear is fixed, then this point where the sun and the planet gear are meshing must not be moving, because the sun gear is not moving, and the planet gear meshes with the sun gear at that point. So the tooth that meshes with the sun gear must not be moving. So if that point there is not moving, we can treat this planet gear as if it were rotating about that fixed point right there. We know that velocity of this point is 1 meter a second, and we can find this radius of the planet gear, so we could find the omega then. So the velocity c is the omega of the planet times the r of the planet. So therefore the rotational speed of the planet gear is 20 rads per second. Step 3. Now let's find the velocity of point M with respect to point C as if C were fixed. So we're going to say, okay, what if point C, the middle of that planet gear, were fixed? What if that were fixed? So in other words, what if this were just a fixed point right there? Let's draw it as if it were fixed. If that were fixed and the planet gear were only rotating about this fixed center point C, could we find the velocity of point M, this velocity of M with respect to C, or in other words, the velocity of point M as if C were fixed? Well, of course, we can just do that by taking the omega of the planet, multiplying it by the radius, and we see that we have the velocity of point M, if C were fixed, would be 1 meter a second. Okay, now let's find the actual velocity of point M, because we know that point C really isn't fixed. Point C happens to be moving. Point C is moving at 1 meters per second, and point M is moving at 1 meters per second if C were fixed. So let's do the superposition method. We will say the velocity of M is the velocity of C plus the velocity of M if C were fixed. So that's superposition. We're superimposing the translational component on top of the rotational component. So we see that the actual velocity of point M is 2 meters per second. So now let's go to step 5. Let's find the angular velocity of the ring gear. Well, there's the ring gear. We know that the actual velocity of that point is 2 meters a second. So let's find out how fast that ring gear would have to be rotating to give us that 2 meter per second velocity. We can find that by omega times r is velocity at M. So let's solve for omega of the ring, which is 11.4 radians per second. So let's just summarize. If the planet carrier is being driven at 8 radians per second, the ring gear will travel at 11.4 radians per second. What kind of ratio is that? Well, that is about a 1.42, 1.43 to 1 ratio. Okay, let's see if you could figure this out. Which equation could be used to find the velocity of the center of the gear, C, if the velocity A is known? In other words, if we know the velocity at this point A, in other words, if someone is pulling this cable at a known velocity, let's find out how fast this point at C is moving. How would we find that? I'll give you just a few minutes to think that through and make your guess. Okay, the right answer is B. If I look at the velocity of A, which is this point right here, isn't the velocity of A, the total velocity at A, made up by the fact that the gear is translating and rotating? So this is again the superposition. If I wanted to write an equation for the velocity at A, I'd have to say, well, what if this gear wasn't rotating, it was only translating? And then I would say, well, what if it were fixed here and only rotating? And then superimpose the two on each other. So this is if it were only translating. This is if it were only rotating. Add the two together, and we find out the total at A. And of course, if we knew A, we could just solve for the unknown velocity C. Okay, let's take a look at one more example of this relative motion analysis of these linkages. here's a crankshaft, and that's rotating at 500 radians per second about a fixed axis passing through A. So there's the 500 radians per second, and it's going in this counterclockwise direction. And this point A is fixed. Let's now find the speed of the piston at this instant that's shown. Now, our logic can say if this is rotating counterclockwise, this piston will be moving downward. So let's take a look at our strategy. If you remember correctly, we will always start with the point we know, and we will work toward point B, and then work toward point C. And then we will write an equation of point C so that we can solve for some of these unknowns. And so we start with the point A going to point B. We know this omega. Okay, so let's take a look at this. First, let's draw this diagram of link AB. So there's the link AB. We know that point A is fixed. We know we have an omega AB, and so we're basically saying we know it's fixed about this point here. This is fixed. We know it's rotating at 500 rads per second in this direction, so this velocity certainly will be straight down. We don't even have to do our cross product on this one. So if I take this omega of 500, multiply it by this radius of 0.1 meters, then I will get my velocity. And of course, we didn't have to do this cross product. They're doing this cross product. We didn't have to do that. We know it was going to be just in the I direction, just from our logic. And we knew that it was the 500 times the 0.1 meters. And that gave us the 50. And how did we get the negative? Well, we knew that if it's rotating this direction, it's going to be pointing down. So we didn't even have to do the cross product. We knew that it was just going to be a negative 50J. Okay. Now let's consider this link BC, this connecting rod. Well, we know that the velocity of point B is moving straight down. But let's take a look at what if this were fixed. What if B were fixed? Could we find the velocity of point C if B were fixed? So this is where this relative velocity equation comes from. We say, what is the total velocity at point C? Well, it happens to be made up of velocity B, which is the translational component here. And then we could take this section, which basically pretends that it's fixed about point B and only rotating. We take omega VC cross with the R going from B to C. So there is our 50J, which is our velocity of B, and here is what we would get if we did the cross product. And notice the omega BC is an unknown. We didn't know that, so we just left it in the unknown when we did our cross product. Okay, so we come up here with a vector. This is our vector if we were to combine the J components here. And what about this X component? This total velocity at C, they're saying, is only in the J direction. Notice here, they said it's only in the J direction. Does that make sense? Do we know that this point C is only going to be in the J direction? Well, of course we know that, because it's connected to the piston, and the piston is forced to move in this cylinder. So it can't have any X direction motion. It can't have any of this because it's constrained that way. So we know that this 0.433 omega BC has to be equal to 0 because the I component of the velocity is 0. So that tells us immediately that omega BC is 0. And if omega BC is 0, then this portion drops out and we're only left with velocity c of negative 50j. There we go. So we use this relative motion analysis to figure that out.